approximately 99.99% of my free stream velocity. This physical distance is called as the boundary layer thickness due to velocity, or the hydrodynamic boundary layer thickness. Okay, so I'm going to have a velocity profile, which I'm going to draw here. This velocity profile says that at a certain distance away from the surface of the plate vertically, if I set up a coordinate frame, x-axis being horizontal, y-axis being vertical, at a certain distance away, the fluid velocity is going to reach the free stream velocity. So this last arrow here is approximately equal to u infinity, 99.99%. In between, I see that there is a velocity gradient, because this is now velocity as a function of the vertical distance y from the plate. If I am on the surface of the plate, the velocity is 0, the fluid velocity is 0. If I am at a certain height away from the plate, the fluid velocity is changing. Slowly it reaches the free stream velocity. And this height of the fluid, starting from the surface of the plate to where you reach the free stream velocity, is the boundary layer thickness, delta H. So delta H is the hydrodynamic boundary layer thickness, and we're going to spend some time on this in the future. Hydrodynamic boundary layer thickness. And what do you think is going to happen to the temperature? You see, the lowest layer of fluid molecules are stuck to the plate. And I'm saying that I'm assuming steady conditions. So after a certain amount of time has passed, what's the temperature of the lowest layer of fluid molecules? It is the temperature of the surface. Which means that as I keep going further and further away from the surface of the plate, the temperature of the fluid molecules will now become lesser and lesser and lesser until it eventually reaches T infinity. So just like you have a fluid boundary layer thickness, you're going to have a thermal boundary layer with its own thickness. So there's going to be a temperature profile that is developing, and I'm going to draw it on a separate figure here. This is Ts. Temperature we're going to is a scalar. Okay. So no arrows. So this is T infinity. As the fluid is coming and meeting this plate, meet and greet, the lowest layer will have the same temperature as the temperature of the surface. And as I keep going further and further away, at a certain point, the temperature of the fluid will be approximately T infinity. Again, 99.99%. So if I go up here, so starting temperature is Ts, ending temperature is T infinity, and this distance from the plate surface to where the temperature reaches T infinity is delta T. And that's called as the thermal boundary layer thickness. Boundary layer, I'm going to say, is BL. So thermal BLT. It's a lunchtime. And you see, many things can happen. The thermal boundary layer can be thicker than the fluid boundary layer. The fluid boundary layer can be greater than the thermal boundary layer. They could be equal to each other. All of this has great consequences on heat transfer. And as you know from fluid dynamics, the study of boundary layers is really complicated. It's easiest for flat plates, but then all hell breaks loose if you start looking at curved surfaces. It's much more complicated. And so people have to resort, I know a few of you are shaking your head. We are going to go through that though, unfortunately. So what people resort to is empirical analysis, experimental. You cannot come up with an equation to describe these things. Okay? So what do we do in convection heat transfer? We do the following. So first things first, when a fluid meets a surface, two things can happen. A thermal boundary layer, a velocity or a fluid or a hydrodynamic boundary layer. Two things. How is the heat transferred? If I say the plate is hot and the fluid is cold, how is the heat transferred? It's transferred in the following manner. The lowest layer of molecules are stuck to the surface, which means that at the bottommost layer of the surface, the heat transfer is in the form of conduction. Because you see there is no bulk motion at the bottommost layer. But then as I keep going further and further up, you see that the velocity starts increasing, becomes equal to the free stream velocity, so there is bulk motion that is going to take place. So all the heat that is accumulated at the bottom is going to be advected into the free stream due to bulk motion. So convection is two things going on. Is conduction at the surface, to the first layer. In reality, this is called diffusion because this conduction can be time dependent. We will look at that at some point in time. Plus, what we call as advection, which is the transfer of this heat from the bottommost layer onto the other layers due to bulk motion. From bottom to other layers due to bulk motion. So a very complicated phenomenon. And this depends on a lot of parameters. It depends on whether the flow is laminar, depends on whether the flow is turbulent. If the flow is turbulent, good luck to you. If the flow is laminar, we have some chance of understanding what's going on. So all of these hopefully bring back good memories of fluid dynamics for you. Okay. And the equation, for the time being, that we're going to use to define convective heat transfer rate is the following. Rate equation for convection comes from Newton's law of cooling. The law is as follows. Q convection is going to be the surface area available for heat transfer, which is the area of the plate that is exposed to the fluid. So some A times a constant, but keep in mind that guy is not a constant. It's going to be called as the convective heat transfer coefficient times the temperature difference, whichever is hotter minus whichever is cooler. So in this case, I'm assuming T is greater than T infinity, so this is Ts minus T infinity. Very last thing that I want to write before I leave you is the following. So H convective heat transfer coefficient The whole damn aim of convection is to find out what this guy H is. That's all it is. Because H is a function of so many things. It's a function of the temperatures, it's a function of the velocity, it's a function of the thermal boundary layer thickness, the hydrodynamic boundary layer thickness, it's a function of Reynolds number, it's a function of the fluid properties, density, viscosity, it's a function of how rough the surface is, so the friction coefficient. You see, it is so complicated. It's a function of so many variables. So many people's lifetime work is to actually find out, for a given set of conditions, what is this convective heat transfer coefficient. If I can find it, then it is just plug and chug. Okay? Thank you.